Up to now, we've looked at execution time, temporal complexity. It's also possible to measure memory use, and this is called spatial complexity. So instead of time, the question is how much memory is used in the program for input size n. Spatial complexity is a little bit more subtle than temporal complexity because there are two ways to measure how much space a program uses. There is active memory and there is memory consumption. So the active memory is how much memory all the data structures of the program need at a particular point in time. So this is usually given as a function of the time. So during the execution, it might need different amounts of memory at different times. And instead of giving the worst value for the maximum value over the whole execution, it's usually much more interesting to have a function because sometimes the program needs more memory and other times it will need less. So that's the active memory. Memory consumption is something quite different. When the program is doing its calculations, it needs memory words. It needs fresh, new memory words for the temporary data structures it's using. Not all of these data structures are needed for a long time, but they're needed right now for the calculations. So the program will be allocating memory words at a particular rate. It's words per second, okay? Whereas the active memory is a number of words, the memory consumption is words per second, allocated per second. When the programming is doing computations that need a lot of temporary data, the memory consumption will be higher. When it needs less temporary data, the memory consumption will be lower. Let me give some examples to fix your intuition. So active memory, let me give an example of an in-memory database. Okay, so I have a lot of RAM memory in my system. I have filling it up with a database that's all sitting in RAM, nothing on disk. So the active memory is large. Okay, the amount of data structures needed by the program, it's basically the whole database and it has to stay there and it's large. But the memory consumption is small. Why do I need to do memory consumption? It's when I do a query. When I query the database, I will basically look up information. So if I'm just looking up something, I need almost no memory consumption. I just need to look up existing data, not change it. When I'm updating, changing things, I will change a small part of the database. So in any case, the memory consumption will be small. So that's my first example. The other example is just the opposite. It's a simulation, and typically simulation programs behave like this. So let's say we have a simulation of molecules moving in a box, and the molecules can bounce against each other, bounce against the walls of the box, and so on. So this program has a large memory consumption. So at each instant in time, it has to calculate the new position of each particle. And assuming that it's doing a very precise calculation, it's a complicated calculation that needs a lot of temporary data. So it has to allocate lots of memory for these calculations. But once it calculates the position of a particle, it doesn't need the memory anymore after. So the active memory is small. All it has to do is store the positions and velocities of the particles. So in the simplest case, it would be 3 real numbers for XYZ position and 3 real numbers for XYZ velocity, and that's it. So the active memory is very small, but the memory consumption is very large. That's a second example. So you can see the quite different meanings of these two concepts and where they're useful. Let me give another kind of tongue-in-cheek intuition on active memory and memory consumption. It's for human beings. So your active size is how much you weigh, how many kilograms, and your food consumption is how much you eat in kilograms per day. Notice the amount, kilograms, and the kilograms per day. So the food you eat is used by your metabolism to stay alive, but only a small part of it actually becomes part of your body. Even if you eat 2 kilograms of food per day, including fluids, After 100 days, you will not weigh 200 kilograms. So here's another way of looking what happens during the execution of program in terms of memory. So when we look at the life cycle of a single memory word, so we have a memory word, how does it live? Well, it starts out by being free, so it's in the free set, and then the program needs it, so it's allocated, so it moves to be active, so it's used in a calculation, there's useful information stored there, and at some point the program does not need it anymore, so it doesn't reference this anymore, there's no more pointers to it, so the poor memory word becomes inactive. And after a while, a lot of inactive memory words are kind of hanging around, and there's an algorithm that collects them. This is called garbage collection, and then it becomes free again. So there's a kind of cycle, the memory words going from free to active to inactive to free again. Sometimes we can move them back from active to free immediately. For example, if they're on a stack, and if we deallocate a stack, we can move them directly back to free. But very often, if they're part of complicated data structures, it's not so easy to do that. We don't really know right away when they're inactive because it depends on all the pointers in the program. So we need some kind of a program called garbage collection. So active memory is basically how many memory words are sitting in the active state. Memory consumption is how many words per second are moving from free to allocate. Okay, from free to active, sorry. So this is basically how the memory management works in a real system. Let me make a quick connection with semantics. Semantics, which will be the topic of next week's lesson. In fact, all of what we've seen in terms of computational complexity can be calculated through the kernel language and through the semantics we will see next week. The temporal complexity is the easiest. Each instruction in the kernel language has primitive operations, and we can know how many there are. We just have to count them. So when the program executes in the semantics. We can also compute the spatial complexity, the memory consumption, and the active memory. So the memory consumption is calculated by counting the number of words that kernel instructions allocate. We know that. So that's pretty easy. The active memory is actually harder. We have to figure out which part of the memory is active and which part is inactive. And the way to do that is to start from the semantic stack. This is a core part of the semantics that we'll see next week, and follow all the references, and everything we find is active, and everything we don't find but is still sitting in memory is inactive. So the semantics we will see next week, we can use it to calculate both temporal and spatial complexity, and we can even do garbage collection in the semantics. So garbage collection is not a mysterious operation done by the runtime system. It's a very simple, clean thing that you can easily understand in the semantics.